Welcome back to sixth lecture, and we are discussing fixed point iteration methods. So let me share my slides, and we will study one of the important methods, which is a part of the fixed point iteration methods. So I hope you can see the slides now. This method goes by name of two mathematicians, Newton and Raphson. The Wikipedia page for Raphson actually says that Newton had devised a method, but Raphson made some subtle changes, and that way the method had faster convergence. So the method that we learn these days is actually the Newton-Raphson method. So it is indeed correct to mention both the names. So this is simply a particular fixed point iteration method. We know that whenever we have a root finding problem, we convert it into some fixed point iteration problem by introducing some function, and the Newton-Raphson method is introducing the fixed point function in a particular way. That's what this is about. So what we assume that the function which is defined on AB to R is twice differentiable. This is one small but very important change from the earlier condition. The earlier condition was simply that function be continuous. Here we ask that the function be differentiable and its derivative be also differentiable, so that we have a slightly better Taylor approximation to the function. That's the basic point. Okay. So suppose there is this point P which is to be found, but it's a solution to the equation fx equal to 0 that we start with. And if you have any other point P naught in this interval, then Taylor's theorem will give you an approximation. So we have that f of p is equal to this f of p naught plus p minus p naught into f prime p naught plus p minus p naught whole square upon 2 f double prime at some point xi. So what we are really looking for is that we have a linear polynomial, that f p naught plus p minus p naught into f prime p naught, and that approximates the value of f at p. But there is an error, and that error is given in terms of this p minus p naught whole square f double prime xi for some xi. So this is really not an approximation. This is the equality, when that xi is something that we don't have any control on. But if you assume that p naught is close enough to p, if we assume that p and p naught are very close, then the square p minus p naught square is very close to 0, and therefore we will ignore this term containing the square of p minus p naught. So in this method, this is very important. This is an assumption that we have, that p naught is very close to p, and therefore this p minus p naught square upon 2 into f double prime at some xi, that can be ignored. So we don't have any dependence on this unknown point xi. But once we put that to be 0, then what we are left with is only the constant part f of p naught plus the linear part p minus p naught f prime p naught. This is approximately equal to 0 because that is approximately equal to f of p. So this is what we have, f of p naught plus p minus p naught f prime at p naught is approximately equal to 0, or if you simplify this, this will give that p, which is the point to be found, is approximately equal to p naught minus f p naught upon f prime p naught. Okay, so we have an approximation to the point p. Starting from p naught, we have bettered it, we have improved it by subtracting this value f p naught upon f prime p naught. Now this is how Newton-Raphson method begins. It starts with a p naught and then generates this sequence Pn by Pn equal to Pn minus 1 minus f of Pn minus 1 upon f prime at Pn minus 1. So it takes an approximation and improves the approximation by this small correction, and it keeps on doing that until we have our convergent sequence to converge to the point P. So note, of course, that if your derivative vanishes at some Pn, then you cannot have the Newton-Raphson method. Then the method stops because you can't divide by 0. So if the derivative vanishes at some point, then we cannot work with this. So that is one small care that we have to take. It is good to assume that the derivative at p is non-zero, because these pn's are coming closer to p, and if the derivative at p is non-zero, then for close enough points the derivatives will be non-zero on pn also. Okay, so that is one small assumption that we will have, which will make our Newton-Raphson method more effective. So let's try to understand this method graphically or geometrically. Okay, so we will actually see one image in the next slide, and that will tell you how these approximations are obtained using tangents. Naturally, whenever you have the derivative is very intimately connected to tangents, and what happens is that whenever you start with the initial approximation p naught, what we do is that we look at the point p naught f p naught, which is on the graph of the function. Okay, so it's the point in R2, it's the point on the graph of the function whose x coordinate is p naught and y coordinate is f p naught. Then you take the tangent at that point. So the tangent will cut the x-axis somewhere, and once it cuts, that is where we are assuming that the slope is non-zero. If the slope is zero, the tangent will be horizontal and it will never cut the x-axis. Okay, so once the tangent cuts x-axis, you take that particular point, the x-intercept, that is taken as p1. Then you take the point again on the graph, which is p1 comma f p1, and repeat the process. You take the tangent at that will intersect the x-axis at the point p2, and then we continue. So this is the way this method works, and this is our picture. We see that here we have p naught on the the leftmost point, which is denoted on the line, and the value at p naught is negative, so the point on the graph is below x-axis. You have this tangent line which intersects the x-axis at the point p1. So the x-intercept of this tangent at p0 comma f p0 is p1. You take its value and then take the corresponding point on the graph. So since the value at p1 is positive, the point on the graph is above x-axis, and we take the tangent once again, and we see that although it seems that from p0 to p1 there is not much change compared to p, but from p1 the next point p2 is very close to your zero, and this is what is going to happen many times, that this method, whenever it is convergent, it will converge very fast to the root that we are looking for. Okay, so this is how this method works. Once again, you start with p0, take the point on the graph, which is p0 comma f p0, take the tangent, intersect the tangent at some point with the x-axis, that gives you the next approximation p1. Take its point on the graph, take the tangent and intersect it again with the x-axis, that gives the next approximation p2, and then we continue. So this is how we have. If you remember, we had considered this example in our last lecture, x cube plus 4x square minus 10. This was the function, and we wanted to find the root for this function. So we wanted to solve fx equal to 0. We had converted into a fixed point problem in 3 ways, but at the end of the lecture I told you 2 more ways which were faster. So A, which is g1x, which was simply obtained by taking x minus fx, which would be the most simple-minded function that anybody can think about to start from the root finding problem to the fixed point problem. And then we had this slightly complicated function g2x, we had g3x, so the g1x and g2x did not work for us. G1x was going to infinity, so that gave you a divergent sequence. It did not take the interval that we were looking at back inside it. G2x actually gave you complex numbers at some stage, so even G2 did not work. But G3 worked beautifully. G3 was a very nice function. And then I said that you can look at G4x, which is slight modification of G2 really. And this final example, which very close to the function you started with. So your numerator is the function x cube plus 4x square minus 10 and denominator is the derivative of the function. So here this last approximation, the last fixed point problem, that is the one which is given by the method of Newton and Raphson. And here now we have a complete table of approximations. Earlier in our last lecture, I showed you only the ABC, but we can look at the D part as well as the E part. C, D, E, all three converge to our solutions. C converges at the 30th iterations, whereas D converges at the 15th iteration already. And you look at E, which converges to the solution at the 4th iteration already. So E is very powerful. That was given by Newton-Raphson, and that's a very, very powerful method. Let's look at one more example. Suppose we consider this equation fx, which is cos x minus x, and we equate this to 0. So we are looking for a root finding problem. Fx equal to 0, where fx is cos x minus x. So we are looking at cos x equal to x, and therefore we convert this root finding problem into a fixed point iteration problem. Cos x equal to x would be one very natural way that you can convert it into a fixed point problem. So that is our first way. And second way is that we are going to use Newton and Raphson. So that will be x minus the function on the numerator, which is cos x minus x, and the denominator is minus sin x minus 1. Okay. Now we have to find some good initial approximation P naught. Without our initial approximation, this method will not work. So we have to find a good enough initial approximation. What initial approximation should we take? What P naught should we take? So let's look at the graphs. Cos x and x, these are some very simple-minded functions. Let's look at their graphs. Y equal to cos x, which is this function. It will start from 0, where the value of cos x is 1, and then at pi by 2, the value of cos x is 0, and then it will go down below the x-axis. Whereas y equal to x cuts this somewhere between 0 and 1. And if you look at the picture very carefully, if you take pi by 4, which would be slightly ahead the fixed point, that would be the thing which would be a good approximation. That is something which is a reasonable thing that we can take. It seems reasonable to take the initial approximation at pi by 4. So we have 0 to pi by 2. 1 would have been also a good point possibility, but it is further away from the fixed point than the point pi by 4. So we will take pi by 4. Remember that there are two fixed point methods. The first one is g1x equal to x, and the second one is the Newton-Raphson method. And these are the results. So when you start with the same P naught, which is 7, 8, 5, 3, 98, 16, 35, which is pi by 4, then in the fixed point iteration, if you look at this image, we had started from a number which is slightly bigger than the fixed point, and when you take its value and take the x-intercept, then you are going to be slightly lower than the x-axis, the cos of that, because you have to take cos of that. The fixed point iteration method is given by g1x equal to cos x. So I start with pi by 4, which is somewhere here, just below 1. And when I take its value, here that value is lower than the fixed point. So I would be somewhere on the lower side. My next approximation P1 will be smaller than the fixed point. Then I take its value again. Now it has gone above the fixed point. So my P naught is ahead of the fixed point. P1 is below the fixed point. P2 has again gone ahead, but lower than P naught. So here if you look at P naught is 7.8 something, P1 is 7.0 something, P2 is 7.6 something. So we have again gone ahead, but slightly lower than P naught. We haven't done as bad as the initial approximation P naught, but it is still not good enough. Then you apply the iteration method once again, and P3 is 0.72. Sorry. P4 is 0.748. P5 is 0.732. So this looks like a pendulum. that you are going ahead of the fixed point, then you come back and become smaller than the fixed point, then you go ahead by smaller margin, then come back, but again you are wrong by smaller margin further, and so on. And when the pendulum stops, that's when you are going to get your fixed point, but that may take a long time. Whereas the Newton-Raphson method at the third iteration itself has given you the fixed point good enough for first 10 digits. There might be changes in the third and fourth thing after you look at the 10 digits after the 10th place. But as far as 10 digits are concerned, third iteration already gives you better results. So it is really evident that some of the natural fixed point problems that you might convert your root finding problems into may not be good. And you have to therefore convert it into the Newton-Raphson method, because that is evidently better than the fixed point iteration method. And it is, however, important that this p minus p naught should be very small. Only then you can cancel that p minus p naught square term from the Taylor's polynomial, Otherwise, if your p minus p naught is not very small, then the approximation will have some error. You might happen to be lucky sometimes, and even if you have a bad approximation, the first few iterations might bring you closer to the zero, and then you will have a rapid convergence. That may still happen. But it is important to note that there is a very nice theorem why Newton-Raphson method works when you are taking p minus p naught to be small enough. And the theorem statement is here. Suppose we start with a function which is twice differentiable. Also assume that you have a point p in the interior, which is a root for your function f. And most importantly, that the derivative at p is not zero. I told you that this is one very important condition that we have to assume to make the Newton-Raphson method work faster. Okay. So we have this condition that the derivative at p is non-zero. If that happens, then there is a delta positive. This sounds like some calculus theorem, some real calculus theorem, because there is a delta which has come. So once you have the derivative to be non-zero, there is a positive delta such that in this neighborhood p minus delta and p plus delta, you take any initial approximation. Any initial approximation that you take within this delta, the Newton-Raphson method will give you a sequence which converges to p. This is a very important theorem. It tells you that once you are close by, it doesn't matter what p naught you take. In that range, any p naught will work. And once again, the proof of this theorem is not really difficult, but I will not be doing this proof. You can look at this proof in many numerical analysis books, and we will not be asking these kind of proofs in the exam also. But it's important to know the statements. It is important to understand the statements completely. So the statement says that, first of all, there is the twice differentiability. Then you are assuming that there is a root where the derivative doesn't vanish. So with this hypothesis, we get that there is a delta which has a nice range, such that in that range of 2 delta, so delta here and delta there, so in that range you can take any initial approximation, and Newton-Raphson will give you a sequence which converges to p. Okay, so this is a very important, but although it's a theoretical result, but this theorem says that under reasonable assumptions. So what are the reasonable assumptions? The reasonable assumption is that the derivative doesn't vanish. Under this assumption, Newton-Raphson method converges, provided that a sufficiently accurate initial approximation is chosen. So you have to choose that p naught within that delta range of p. That is important. Okay. So although it is important theoretically, but it's not really applied in practice, because we don't know how to compute this constant delta. This constant delta it depends on the function value at p, the derivative value at p. Because once f prime is non-zero at p, there is a small interval around that point p where the modulus of f prime remains non-zero. and that's where we get the delta from. So it is only a theoretical result. It guarantees existence of delta, but it doesn't tell how this delta can be computed. Okay. So in practical applications, what we do is that we just choose an initial approximation which looks closer when you look at the graph, and then we generate successive approximations. So either you will get a quick convergence to root, or the convergence will be unlikely, and that will be very clear in first few steps already. Okay, so this is what is good about Newton-Raphson method, that you start with an initial approximation, compute the derivative, do the fixed point iteration, and you will either have a quick convergence to the root. It will be very clear that the approximations are stabilizing, you are getting a fixed point very quickly, or it will also be clear that you are not getting a fixed point. So this is the nice thing about Newton-Raphson method. However, there is one point that you have to compute the derivative, and we will introduce another method in our next lecture which will circumvent this problem. So in that lecture we will introduce this another small variation of Newton-Raphson method, and until then we will stop at this time. Thank you.